I will use. So G is going to be rank 1 simple Lie group. So if you quotient out by maximal compact subgroup, this is going to be rank 1 symmetric space, and it's also going to be negatively curved contractible manifold. So if G is SON1, X is HN, yeah, and gamma is, so G is also the isometry group, of X, and gamma is going to be a discrete subgroup. And if you were here last Friday, Fraczyk-Gelander outlined a proof of the following result of himself. Why am I writing it like this? Of himself and Nikolai Fraczyk. That if this was not rank 1 but higher rank, if this quotient manifold M equals X mod gamma has infinite volume, then it has unbounded injectivity radius. So unbounded injectivity radius means, like maybe you have some parts here where the injectivity radius is bounded, but then you have like some other part when you can injectively embed like super big balls. Yeah, so bounded. So for all R, there exists a point on this manifold where the injectivity radius is like bigger than R. Okay, so I want to discuss rank 1 analog of this theorem, except that like it's false. Because so remark, so in rank 1 this is false, and an example, so if you have a co-compact lattice in hyperbolic space is and normal subgroup, then Hn mod n has bounded injectivity radius. So you can prove it as an exercise or something, but I'll draw a picture for when this is like so gamma is a lattice in SL2R, and gamma mod n is Z. So this is a cyclic cover of so this is a cyclic cover of a compact surface like this. Yeah, and this is bounded injectivity radius. And so the offset is like in higher rank, Margulis' normal subgroup theorem says that lattices in higher rank Lie groups don't have normal subgroups, and in rank 1, they're hyperbolic groups that have lots and lots of normal subgroups. Okay, so this theorem is false. So we wanted to prove something. So yeah, so everything here is presenting as joint work with Arie Levit, and motivated by some questions of Fraczyk-Gelander. Okay, so we want to prove something that's true. So we want to come up with a criterion for unbounded injectivity radius using something, quantitative. So one way to do it is using a gadget called the Laplace-Beltrami operator. So, which I'm not going to define because you don't do it in polite company. Okay, you can Google it, or I'll give you interpretation better ways in 5 minutes. So under Riemannian manifold, M. Okay, so there is something called the Laplace-Beltrami operator, and it has something called eigenvalues, and in particular, it has smallest smallest eigenvalue, and so intuitively, okay, so back to the setting, M is like X mod gamma. So if M is compact, then if M is compact, then this thing is equal to 0. And okay, so I'll present so the first theorem. So myself and Arie Levit. So if the bottom of the spectrum of X mod gamma is strictly less than the bottom of the spectrum of X, this means this group is sort of like maybe not so big as to make this quotient compact, but it's pretty big. Then X mod gamma has unbounded injectivity radius. So this relates sort of a quantitative property of this manifold to a qualitative property. And okay, for those of you who don't like Googling, there's like a better way to think of this condition. Well, to me, it's better. I mean, lots of people in the world spent all their lives studying this spectrum, and they're very noble people. But to me, I prefer to think about this in a different way.
Are you in particular, does this mean that in particular gamma is co-infinite, or you're assuming that gamma is co-infinite?
If gamma is cofinite, then this is also 0.
Oh, okay.
So yes. Yeah. I mean, finite volume things have finite volume hyperbolic manifolds have bounded injectivity radius, right? Because if you're finite volume, you can't have unbounded injectivity radius, because
I don't know what number 0 is.
Yeah, okay. This gets smaller when the manifold gets smaller, when the group, when it gets more compact. Wait, isn't there supposed to be some matrix in there?
In the middle, a pulp in the middle, it's an east. The middle of the board. Yeah.
Oh, sorry, I don't speak French. Okay.
So I think I'm confused. Like, is it supposed to be bigger or is it supposed to be bounded? Because if it is, we want an experiment smaller. If we take through that.
Sorry. Yes. Let me put it this way. Unless yes. Yes. Thank you. This is unless this.
Well, okay.
Yes.
Can it be bigger than it?
No. It's always, this is always, if you quotient by something, you always get less than or equal to. If
it's equal, then
yes. If it's equal, then it's unbounded. Yeah. Okay. So thank you. Yeah. You're. Thank you.
Right, so maybe the way to do that. So
Yes.
in the equality case, what happens?
In the equality case,
It's open, it could be either way.
in the equality case, it could be either way.
Oh.
Yes. So yes, well, it's okay. So I'm gonna. Yeah, I just wanted to. In the equality case, if sorry, yes, if it's yes, if they're equal, then this is unbounded.
Okay.
If in the equality case, it could go either way. Yes. This is the implication. It says
Unless makes it up here.
it's okay. Okay, counter positive.
If it's equals, then it's still big, x mod gamma is still big, so I'm out gamma.
Yeah.
The limit is there, it's smaller than it's similar.
This is
Okay.
yes. Sorry about that. Okay, so I'm going to interpret it now in a different way, and in a sort of quantitative way, and this involves a notion of growth, so growth of groups, which, if you were here last week, Tiani talked about, but so suppose you have discrete subgroup for isometries, and we're going to fix a base point O in X. That's a base point. The so critical exponent or the exponential growth rate of gamma, so is defined this way, delta gamma, so it's the limit as r goes to infinity of 1 over r times log of like the intersection of the ball of radius r around this base point intersect with the orbit of this base point. So this really only makes sense for discrete groups, because otherwise this is infinite, and okay, infinity, I don't know anything about infinity. So okay, yeah, so this is a number. Okay, but it has some very nice properties in this setting. So if gamma is a lattice, so remember lattice means the quotient x mod gamma has finite volume. Delta gamma, so it does not depend on the lattice. So you can interpret it as like the Hausdorff dimension of the boundary of this like negatively curved manifold X. So it's some manifold, it has some boundary. And I'm not going to talk deeply about what I mean by Hausdorff dimension here, but I'm going to say this equals n minus 1 if x is hn, and this equals to 2n if x is the n-dimensional complex hyperbolic space. So in particular for SL2R, any lattice in SL2R has critical exponent 1, right? One is a very, so you can just concentrate in the case H2, and then 1 is a very nice number. And I'm going to call this number, for future reference, I'm going to call it delta of x, because it's really a property of this symmetric space.
is only for rank one, or there's
so the fact that it's independent of it's independent of the lattice. This is true in higher rank. This is also true in like way bigger generality. Yeah.
Okay, it's the dimension of the boundary.
It's dimension of the boundary. So okay, so this is sort of rank one thing in the sense that this is like not the topological dimension of the boundary. It's the Hauser dimension with a certain like metric on the boundary that you get from the Gromov product. Yeah. So for example, in this case, like okay, in this case, like this is one. Like in this case, this equals to the topological dimension for the boundary. In this case, like the manifold itself has dimension 2n. So this is bigger than the topological dimension of the boundary. Yeah. Yeah. Well, yeah, other people should also feel free to ask questions, not just that. Yeah. Okay, so right, and there's a nice relation between this critical exponent and the bottom of the spectrum. So this is due to Elstrott in various levels of generality, Elstrott, Patterson, Sullivan, and Corlett. So Corlett has the most general version, but so lambda 0 of x mod gamma is equal to lambda 0 of x, which is delta of x squared over 4 if delta of gamma is greater than or equal to delta of x over 2, and it's equal to delta of gamma times delta of x minus delta of gamma if delta of gamma is strictly less than delta of x over 2. So these two things match up at this boundary. So this is a continuous function. Yeah, and I think this might clarify Tal's question at least. So okay, or maybe not. Whatever. Yeah. So there's a relation, and so what we actually want to prove in our theorem with Arie Levit is that if lambda if delta of gamma is less than or equal to delta of x divided by 2, then x mod gamma has unbounded injectivity radius. So like the opposite situation of this is when gamma is a lattice. So delta of gamma is equal to delta x, which is not less than or equal to delta x over 2, and then x mod gamma has definitely has bounded injectivity radius.
How general is this relationship on this board?
How general is this relationship? This is on the nose it works for rank 1 symmetric spaces, and in higher rank there's more complicated formula. And in more general negatively curved manifolds, there's like some bounds involving curvature and this. Okay. Right. So this theorem is sort of sharp in the sense that
So can we ask?
yes.
So in which case is the lattice case?
The lattice case is so the lattice case, so these things are equal, so this thing is equal to 0 in the lattice case.
So you can, the growth exponential must be.
The exponential growth of a lattice is delta of x. So in the lattice case, the bottom of the spectrum is 0.
Yeah, but delta of gamma, so I'm sorry,
Delta.
is delta of gamma less than delta of x?
No, for the lattice, delta of gamma equals delta of x.
That's why I ask.
So when you're equal to something, you're not less than half of it.
I know. That it could be in the first line, right?
Yes, yes, yes. You're in the first. Yes, this is.
I'm confused.
Sorry.
Just get
Yes, yes, yes. This is. Yes. Yes. Thank you very much. Yes, I'm just dyslexic or something. Yes. This is the right. Everything. Sorry. So. Okay. Okay. So I want to say that this theorem is sharp, at least for. So this half, this is sharp, at least for SL2R, or for x equals to H2, because in any co-compact lattice, in any co-compact lattice, yeah, gamma, there are a sequence of normal subgroups n sub n with delta of n sub n converging to, I guess, yeah, converging downwards to delta x divided by 2. So this is a theorem of Matsuzaki, I guess, yeah, so Banfer-Taylor. That's like one person, Matsuzaki and Taylor. Sorry? Yes. Moving higher. So this is optimal because, you know, normal subgroups, like I wrote here, have like normal subgroups of lattices have bounded utility radius, and you can have normal subgroups of lattices with critical exponent like as close to half of like delta x as you want. Okay, so everything I stated so far, so there's nothing random in it. This is like completely geometric. But this is a theorem about stationary random subgroups. And in order to phrase it as, you know, phrase the theorem about stationary random subgroups, I want to do it in a very broader setting. So this is going to follow from a theorem about stationary random subgroups, which is true in much bigger generality of Gromov hyperbolic spaces. So, okay, before I state this theorem, maybe, yeah, let's set things up. So let X be proper geodesic Gromov hyperbolic space. So the two sort of examples of these things you should keep in mind, if you don't know what these are either rank 1 symmetric spaces or Cayley graphs of hyperbolic groups, like Cayley graphs of free groups. Anyone wants me to define what a Gromov hyperbolic space is? Okay, I mean, yell out if you do. My co-author who's writing this who's watching this in Zoom is like explaining me that I'm doing things wrong. So okay, X is a proper Gromov hyperbolic space. And I think there's a delay because so okay, and you assume that the isometry group of X contains co-compact lattice gamma 0, so it means there is some group which acts discretely and co-compactly. So maybe the whole isometry group itself is a co-compact lattice, maybe the isometry group is a Lie group which contains co-compact lattices, but in any case, and let mu be a probability measure. So mu is a probability measure on this lattice gamma 0. And we assume some things of it, like the support generates gamma 0 as a semigroup. And you also assume that mu has finite second moment. Finite second moment, so this means like you take the sum over gamma 0 distance in X, this thing squared, mu of G, and this is finite. So in particular, if your support is finite, then you definitely have finite second moment, but we're going to have the occasion to work with infinitely supported probability measures as well. So this is important. Okay. And let mu be mu stationary random subgroup. So what's a stationary random subgroup? It's a measure on the space of subgroups of I sum X. So I'm going to call this I sum X G, which is stationary with respect to the conjugation action. So the action of G and its subgroups by conjugation. Okay, so now comes the theorem, and this is theorem of myself. So same two people. So under these conditions, either or maybe I should say so for mu almost every H, so H is a subgroup, this is a measure on subgroups. So mu almost every H, we have one of the following two things. So the first case is something really boring. So H is contained in the amenable radical of G. So an amenable radical of G, this is the largest amenable normal subgroup of G, and So for if this is like just equal to the identity for rank 1 simple Lie groups, because you know they're called simple for a reason. So this AD for G equals rank 1 Lie group. And this is finite for you know, if G is hyperbolic group. Okay, so that's boring. So now less boring case. The critical exponent. So okay, so I want to say that the stationary random subgroup is either basically trivial or it's really big. Maybe not as big as a lattice, but like still pretty big. So delta gamma is greater than or equal to delta x divided by 2. Sorry, no, this is not true. I'm getting ahead of myself. It's greater than or equal to entropy. So L of mu, H of mu over 2 L of mu. So this is the entropy, and this is the drift of the random walk. So how do you define the entropy and drift for those that were not in Chinese and Laszlo's lectures last week? So I read it here. So the drift is like the average. It's like the average amount that the distance increases after one step. So it's the limit as n goes to infinity. So distance of and H of mu is a measure of complexity of convolutions of this random walk. So this is again 1 over n times minus sum over G log. So, you know, this is just literally like the information theoretic entropy of the nth convolution of mu. And then, you know, when you take convolutions, when you take like higher convolutions, this grows. So you normalize so that like this converges to something, and both of these limits exist. Limits exist for almost every like sequence GI, like for any almost every trajectory of the random walk. Yeah. Okay, well, this exists for almost every trajectory of the random walk. This just exists. Yes, so I'm going to this next. Yes, so thank you for asking. Because I'm about to say this, so I shouldn't use this board, right?
Like only stationary inside gamma, like you only take you.
It's a subgroup. It's stationary. So the measure is supported on in gamma, but the stationary random subgroup, like they're not subgroups of gamma. They're subgroups of G. Yeah. So and you know, so I mean, and of course, okay, if you like Tafik said last week, if you take a different mu which has the same percent boundary, then it has the same stationary random subgroups. So it doesn't really have to be a subgroup of gamma.
I mean, they are also subgroups and you.
They're not subgroups of gamma. They're not subgroups of gamma. Yes, you can't. So you take So you take subgroups of G. Yeah, so yeah. Just they're stationary with respect to a measure in gamma. So you can think of it like you're conjugating by elements of gamma. But yeah, but the subgroups themselves, they're subgroups of G. I don't know. Yeah, this board. Yeah, I'll use that board. So yeah, so important question. Can you choose a measure for which these two are equal? So okay, so in general, okay, in general, no. In general, like I don't know, but for rank one mediums, you can choose discretization of Brownian motion. And in which, so I'm gonna write about this. Oh yeah, so like Chanyi said, this is oh no, this is okay. Yeah, so what do we know about this entropy and drift? So we always know, okay, so first let me, so always true, h of mu is less than equal to L of mu delta of gamma. So this is due to either Fraczyk or wave arch, or I'm not taking sides. So yeah, so this is always true. So if X is a rank one symmetric space, and you can take mu to be discretization of Brownian motion, which is, this is some okay, whatever this is some Brownian motion, is some diffusion operator associated to the Laplace-Beltrami. It's some diffusion process, like continuous time associated to this Laplace-Beltrami operator, and you can take like some discretization of it and this discrete subset gamma zero. But in any case, what's important is that in this case, h of mu is actually equal to L of mu times delta gamma. So in this case, this mu is infinitely supported. So it's a big open question whether you can take mu to be finitely supported such that this equality holds. It's this question is equivalent. So this equality holding is equivalent to like the stationary measure on the boundary of X being the same in the Lebesgue measure class, is the person who has made the most, okay, conjecturally this is never true for finitely supported measures. The person who has made the most progress in this in the last 50 years is in the audience. It's Peter Koshenko. Yeah, so you should back to him. Yes. So
Sorry for losing track. So what's gamma and gamma not? Gamma not was
okay, so right. So you're in the setting or that like this general Gromov hyperbolic setting, and we assume that the isometry group has some co-compact lattice, which we call gamma naught. This is, I guess this this is gamma naught. Yeah, in this setting, yeah.
same thing on
It's co-compact lattice, yeah.
part B.
This in part B here. No.
Oh, it's not.
So in the theorem, yes. So gamma is any discrete subgroup. So gamma naught is a fixed God-given uniform lattice. Gamma is any discrete subgroup. Yeah. Discretization has a finite exponential moment. I mean, yeah. I think Glacher, Hasinski, Mathieu wrote it down carefully. But really, Ledgerpier, okay, yeah. Many. Yeah, so this discretization is due to Leon Sullivan, and then in more generality, Ballman, Ledgerpier, and yeah. Yes. So in general, Gromov hyperbolic setting, not known. So okay, so it's not known if such a mu exists, but there exists a sequence of finitely supported mu n with h of mu n divided by L of mu n converging to delta gamma or delta x. And the way you construct them, you take mu n to be like the uniform measure on balls. Yeah. So this is Guzel Mateus Macron. Okay, so
Yeah, can you clarify?
yes.
So the distance is going to be the what distance? Yeah.
The distance, which distance here?
For the conversion statement, I think it's only true for the what.
No, it's true it's true not just for the word distance in there. Yeah, that part is true.
Yeah.
For any, yeah, it's true here for like for the distance and the metric space where you're acting. Yeah. Okay, so corollary. So a special case of stationary random subgroups are invariant random subgroups, which are like stationary for like anything. They're conjugation invariant measures and sub G. If mu, so if mu is an LS of G equals I sum x, where we're in the setting of this theorem, then almost surely either H is in the amenable radical, or should I call it H? Yeah, okay. Gamma H, oh, I'm confused. But or delta H is greater than delta X over 2. So for rank 1 U groups, you just like, plug in this measure. So Jenny, you seem confused. So this is strictly bigger. So for it's actually much harder to prove the strictly bigger than or equal to. But for like if you're in a rank 1 symmetric space, you can just like plug in this discretization of Brownian motion and get strictly bigger. For general Gromov hyperbolic spaces, okay, if you just plug in this fact, you just get greater than or equal to, but actually there's like other way to prove strictly bigger, not using random walks. Okay, so this is a theorem about stationary random subgroups, from which I want to derive this result about injectivity radius. Okay, so then okay, so great, 0 minutes. So I'm just gonna say, so in the negative 10 seconds that I left, I'm gonna say that like mu n be these measures like Dirac at gamma convolved with powers of the random walk, and then like Sachik said, okay, any Wixter limit of these are stationary, and so if you start with something with small critical exponent, the Wixter limit also has a small critical exponent. So any Wixter limit is the identity. So any Wixter limit is like Dirac at the identity. And if these converge to Dirac at the identity, it means you have lots of points with large injectivity radius. Okay, okay. I'll stop here and you can ask questions.
Thank you very much for those questions or comments.
Yeah.
So I'm just not familiar with the lambda zero. So if you said if you have a lattice, then you get that lambda 0 is 0.
Correct.
If you have, what if you have a co-amenable subgroup of a lattice?
if you have a coimmutable subgroup, then also lambda 0 is 0. So it's actually a theorem. Yes, then also lambda 0 is 0. So it's actually a theorem. Okay, so for like, yeah, it's a theorem that just like n is a subgroup of yeah, well, even like subgroup of gamma. So lambda n is equal to, or delta n is equal to delta gamma if and only if this is amenable. I mean, so amenable is like a Schreier graph, like even if it's not a normal subgroup. This is if and only if, yeah. Okay.
More questions, comments?
Okay.
So you, okay, so the follow-up, so I guess for then relating that back to lambda 0, I guess that equation that you had before, so that give you that also characterizing lambda 0 is 0.
So you could have lambda 0. Wait, when lambda. Okay, so lambda 0 is 0. Yeah, so lambda 0 is 0 when the critical. Yes, yeah, yes. When the quotient. I mean, if you have subgroups of lattices, then yes.
Okay.
Because lambda 0 is completely determined from by delta. So, yeah.
I see.